Okay, so rotational motion. And before this point in the course, we've mostly talked about things moving along lines, or in the case of projectile motion, maybe taken something that's moving along a parabola and kind of resolved it into two 1D motion problems. In other words, two problems of things moving along lines. So now we're going to start thinking about things rotating. We've already seen this in uniform circular motion, things going around in a circle rather than really in a line. Though we dealt with linear variables like the magnitude of the velocity of that car going around a curve. But now we're going to start thinking about things rotating entirely, and we want to define a new set of variables to describe that motion more precisely. Well, maybe not more precisely, but more conveniently. And the diagram I've got here is meant to be a ball on the end of a string. And so it carves out a circle that has a radius r. And we're considering its movement from some initial point here to some final point here. And as you can see, the string sweeps out an angle that is this angle right here, right, formed by those two lines, which I'm going to call delta theta, all right? And so change in angle from initial to final. And at the same time, we know that this thing is going to have go through an arc length, okay? Dotted red line there, okay? That's equal to what I'm calling delta S, and that's equal to the radius of the circle times this angle that's being swept out by the string attached to the ball. And this is an example of an angular displacement, okay? This delta theta. We're going from, well, in our usual sort of XY coordinate system, we're going from 0 degrees up to, I don't know, maybe 45 or 50 degrees there at the final point. So this would be delta theta is equal to 50 degrees minus 0 degrees equals 50 degrees, okay? Now you'll note that I'm not using the correct SI unit here, but just thought I'd portray it in units that we've used before for angle. But to get the equations that we're going to be using for rotational motion to work out just so without extra factors of 2 pi running around, we want to use the unit of radians. You're familiar with radians, right? 2 pi rads per 1 revolution, or per 360 degrees, okay? So, this would be better stated in terms of like something a little bit bigger than pi over 4 minus 0 rads, and then we'd be off with our standard units, okay? But this is the definition for an angular displacement. We've used displacement before, but before it was a change in position, right? Final position minus initial position. And that was measured in meters. And here, we're not so interested in the number of meters that's being covered. We're interested in how much of the circle has this ball on a string completed. Now, once we have this definition of angular displacement, well, we can ask the usual questions. We might want to know how quickly this angular displacement happens. In that case, well, we need to define an angular velocity. And the average, so that's what the little bar means, right? Average. That's not particularly good drawing of that. We can go and get ourselves an eraser. Yeah, make a better one, okay? But this little bar right there is average, means average. So what this is telling us is that if we know an angular displacement and we know the time period during which that displacement occurred, then we know exactly what the angular velocity or average angular velocity must have been for the ball on a string in this case, or whatever object is rotating around a circle, okay? Now, for those of you in engineering physics, I should note that omega at any particular moment in time is the time derivative of some function of the angular position. Okay, so that would be instantaneous angular velocity. And likewise, we can define angular acceleration in terms of how quickly the angular velocity is changing. So the average acceleration, given the symbol alpha, which looks a little bit like a for linear acceleration, is delta omega, this is the Greek letter omega, over delta t, right? So how quickly is the angular velocity changing? That will give you the angular acceleration. And likewise to the other one, the instantaneous angular acceleration is the time derivative of whatever function is telling you the angular velocity, right? So instantaneous version. The other thing that I should point out here is the standard units of these things, though you can certainly figure that out. Once we know that the standard unit for angular displacement is the radian, well, then we know that the standard unit of angular velocity is going to be radians per second, because we always measure delta t in seconds. And we know that the angular acceleration has standard units of radians per second, which is just radians per second squared. Okay? So when we come back for the next video, we'll take these variables and we'll work out a couple of things to do with them. And we'll also outline some properties of rotational motion that are different than you might expect for linear motion. Okay? So I'll see you then.